Welcome to AI Frontiers, where we explore the cutting-edge research that's reshaping our understanding of what robots can do. Today, we're diving into 19 fascinating research papers published on December 20th, 2025, representing some of the most innovative work happening right now in computer science robotics. Picture this. You're sitting in a car that's driving itself, but instead of following pre-programmed rules, it's actually curious about the world around it. It notices when something unexpected happens and thinks to itself, I should learn more about that situation. This isn't science fiction anymore. We're witnessing the birth of truly intelligent, adaptive robotic systems that are both artificial and surprisingly intuitive. Today's journey takes us through three dominant themes that are revolutionizing modern robotics research. First, we'll explore autonomous vehicles that learn without explicit rewards or programming, using curiosity as their guide. Second, we'll examine robotic manipulation systems that understand physics through intuition rather than complex simulations. Third, we'll investigate ethical frameworks that enable robots to make moral decisions about when to follow or refuse human commands. These breakthrough methodologies combine multiple artificial intelligence techniques in unprecedented ways, creating capabilities that were unimaginable just a few years ago. Each theme represents both the maturation of certain technologies and the emergence of new challenges as robots become more capable and autonomous. Computer science robotics represents one of the most fascinating intersections in modern technology, where abstract computational concepts meet the messy, unpredictable reality of the physical world. Unlike traditional robotics, which often focuses on mechanical design or control systems, computer science robotics is all about the intelligence that makes robots truly autonomous. Think of it as the brain that allows a robot to understand what it's seeing, plan what to do next, and learn from its mistakes. This field has exploded in importance as robots move beyond the controlled environments of factories into our homes, hospitals, and streets. The interdisciplinary nature makes it rich and challenging, drawing from artificial intelligence, machine learning, computer vision, natural language processing, and distributed systems. What's particularly exciting about the current state of the field is how it's moving beyond narrow, task-specific intelligence toward more general, adaptable systems that can make ethical decisions about when to follow or refuse human commands. The first major theme emerging from these papers is the autonomous vehicle intelligence revolution, which reflects the enormous commercial and societal potential of self-driving technology. Kanzada and colleagues demonstrate groundbreaking reward-free learning approaches that allow vehicles to explore and understand their environment through environmental curiosity rather than explicit task-specific programming. We're seeing the development of causal knowledge frameworks that incorporate human driving behavior patterns into autonomous vehicle planning systems, recognizing that successful autonomous vehicles must understand and predict human actions, not just follow traffic rules. The research showcases advanced simulation and benchmarking methodologies that create comprehensive frameworks for comparing different approaches to autonomous driving, including both traditional model-based methods and modern data-driven techniques. This represents a fundamental shift from rule-following systems to intelligent environmental exploration, where vehicles actively seek out situations where their predictive models disagree with each other, using that disagreement as a signal to learn more about particular driving scenarios. The second dominant theme focuses on manipulation intelligence that operates without traditional physics simulations, representing a breakthrough in making robots more capable of handling objects in complex, unstructured environments. Researchers demonstrate innovative approaches using physics-free supervision to improve grasp planning efficiency dramatically, showing that robots can learn to prioritize promising grasp candidates without expensive physics simulations. It's like teaching a robot to have good intuition about grasping without making it understand all the underlying physics. There's significant advancement in the development of semantic atomic skills for multitask manipulation, recognizing that many manipulation tasks share common sub-actions or skills. By learning these atomic components, robots can more efficiently generalize to new tasks through compositional intelligence that allows skill combination for novel situations. This represents a fundamental shift from task-specific learning toward more general, composable intelligence that could dramatically improve robot versatility in real-world applications where objects and environments are unpredictable. The third major theme addresses ethical and adaptive robot behavior, particularly focusing on frameworks that enable safe and effective human-robot interaction. As robots become more prevalent in human environments, ensuring appropriate responses to human commands becomes increasingly critical. The research demonstrates sophisticated approaches, including empathic ethical disobedience frameworks, where robots learn when to refuse human commands that might be unsafe or inappropriate. This represents a significant advancement in robot autonomy, requiring robots to balance obedience with safety and social expectations. Beyond software intelligence, researchers are advancing mechanical design through variable stiffness actuators that can safely interact with humans by adjusting their compliance based on task requirements. The integration of reinforcement learning with large language models allows robots to benefit from vast knowledge encoded in these models, while still learning task-specific behaviors through environmental interaction. These advanced approaches to human-robot trust and acceptance show that people actually prefer robots capable of making ethical decisions, as long as those decisions are explained clearly and the robot maintains a respectful, helpful attitude. Several groundbreaking results emerge from this collection of papers, each representing significant advances in our understanding of robotic intelligence and capabilities. One of the most significant findings demonstrates that autonomous vehicles can learn effective driving policies using only intrinsic curiosity signals, without explicit reward functions that specify what constitutes good driving behavior. This approach shows vehicles can explore and understand complex driving scenarios by seeking out situations where their predictive models disagree with each other, serving as a signal for learning opportunities. Another breakthrough involves dramatically improving robotic grasping efficiency without requiring expensive physics simulations. Using simple geometric labels such as inverse kinematics feasibility and collision detection along predefined paths to train neural networks that effectively prioritize grasping candidates. The development of semantic atomic skills enables efficient generalization to novel manipulation tasks by learning common sub-actions that can be composed for different objectives. Diffusion-based action generation combined with video prediction and tree search enables robust planning by allowing robots to explicitly visualize action outcomes before execution. Perhaps most significantly, ethical disobedience frameworks maintain human trust while ensuring safety, demonstrating that robots can learn to make complex ethical decisions while preserving positive human-robot relationships. The papers demonstrate several sophisticated methodological approaches that are advancing the state-of-the-art in robotics research, representing both refinements of existing techniques and novel combinations of different approaches. A prominent methodology involves learned world models that improve reinforcement learning efficiency and safety by learning predictive models of the environment for planning and decision-making without requiring extensive real-world interaction. The strength lies in data efficiency and safety, allowing robots to explore many possible scenarios in simulation before acting in the real world. Diffusion models for generating robot actions represent a significant shift from traditional policy representations, originally developed for image generation, but showing remarkable success in generating diverse, high-quality samples from complex distributions. In robotics, diffusion models generate diverse candidate actions that can be evaluated and refined through additional planning processes. Graph neural networks with attention mechanisms process complex, relational information, particularly useful for applications involving multiple agents, complex scenes, or structured environments. Causal reasoning incorporation enables more interpretable and stable learning by using domain knowledge about causal relationships rather than learning purely from data. Hierarchical compositional learning approaches break down complex tasks into simpler, reusable components, allowing robots to learn at multiple levels of abstraction, from low-level motor skills to high-level task planning. Let me highlight the first standout paper, InDRiVE, Reward-Free World Model Pre-Training for Autonomous Driving via Latent Disagreement, by Khanzada and colleagues. This work addresses one of the fundamental challenges in autonomous driving, the difficulty of designing appropriate reward functions for complex driving tasks. Traditional reinforcement learning approaches require carefully designed reward functions that specify what constitutes good driving behavior. But this is incredibly challenging because driving involves complex trade-offs between safety, efficiency, comfort, and social expectations that are difficult to encode explicitly. The core innovation lies in using latent ensemble disagreement as an intrinsic motivation signal for exploration. When different models in an ensemble disagree about the predicted outcome of an action, this disagreement serves as a signal for epistemic uncertainty, indicating that the vehicle needs to learn more about that particular situation. The framework trains multiple world models simultaneously, each learning to predict future states from current observations and actions. During exploration, the vehicle actively seeks out situations where these models disagree the most, effectively exploring areas of high uncertainty in its understanding of the environment. Experimental results show vehicles trained with InDRiVE demonstrate superior zero-shot transfer to new environments and robust few-shot adaptation to specific driving objectives, potentially solving the reward engineering bottleneck that has plagued autonomous driving research. The second standout paper is STORM, Search-Guided Generative World Model for Robotic Manipulation, which fundamentally changes how robots plan and execute manipulation tasks. Traditional robotic manipulation relies on either model-free approaches that learn through trial and error or model-based approaches using simplified physics simulations. STORM represents a third way, combining the flexibility of learned models with the power of explicit planning and search. The key innovation integrates three powerful artificial intelligence techniques into a unified framework. First, a diffusion-based policy generates diverse candidate actions, exploring the space of possible movements the robot could make. Second, a video world model predicts the visual outcomes of these actions, essentially allowing the robot to imagine what will happen if it performs each candidate action. Third, a tree search algorithm evaluates these predicted outcomes to select the best course of action. The video world model is particularly sophisticated, using advanced neural architectures to predict not just the final outcome of an action, but the entire visual sequence of how the action unfolds. This temporal prediction capability allows the robot to understand not just where objects will end up, but how they'll move through space, crucial for complex manipulation tasks involving multiple objects or requiring precise timing. Experimental results show STORM achieves state-of-the-art performance on challenging manipulation benchmarks while providing interpretable decision-making that can be understood and debugged by human operators. The third exemplary paper addresses empathic ethical disobedience in robots, tackling one of the most socially significant challenges. When should a robot refuse to follow human commands? This research addresses the complex balance between robot obedience and ethical behavior, recognizing that blind obedience could sometimes lead to harm. The framework enables robots to make nuanced ethical decisions by considering multiple factors: the potential risks of following a command, the emotional and social context of the situation, and the long-term implications for human-robot relationships. The approach uses a sophisticated decision-making framework that considers 4 possible responses to human commands: comply, refuse, clarify, or propose alternatives. The robot learns when each response is appropriate based on factors like safety risk, social appropriateness, and the human's emotional state. For example, if a human asks a robot to lift something too heavy that could cause injury, the robot might refuse the direct command but propose an alternative approach that accomplishes the same goal safely. What's particularly impressive is how this work maintains human trust and acceptance while enabling ethical decision-making. Extensive human studies show that people actually prefer robots that can make ethical decisions, as long as those decisions are explained clearly and the robot maintains a respectful, helpful attitude. The framework also incorporates learning from human feedback, allowing robots to refine their ethical decision-making based on human reactions to their choices. Looking toward the future, several emerging opportunities and challenges will shape the next generation of robotics research. The integration of large language models with robotic control systems represents a particularly promising direction, allowing robots to leverage vast knowledge encoded in these models while learning task-specific behaviors through environmental interaction. Development of more sophisticated ethical reasoning frameworks will become increasingly important as robots operate in complex social environments where moral decisions cannot be pre-programmed. Advancement in physics-free learning for complex manipulation tasks will continue to make robots more capable in unstructured environments without requiring expensive computational resources. The creation of standardized benchmarking for multimodal robotic capabilities will enable fair comparison of different approaches and accelerate research progress. Exploration of human-robot collaborative intelligence in dynamic environments will become crucial as robots work alongside humans in manufacturing, healthcare, and domestic settings. These future directions suggest that robotics research is moving toward more general, adaptable, and socially aware systems that can seamlessly integrate into human environments while maintaining safety, efficiency, and ethical behavior. The convergence of multiple artificial intelligence techniques with robotics promises to create machines that are not just tools, but intelligent partners capable of understanding and adapting to the complexities of the real world. This content has been synthesized using advanced artificial intelligence models to provide comprehensive analysis of cutting-edge robotics research. The synthesis process utilized GPT and Claude Sonnet 4 language models for content analysis and generation, ensuring thorough coverage of the technical material while maintaining accessibility for diverse audiences. Text-to-speech synthesis is powered by OpenAI's advanced audio generation systems, providing natural and clear narration for optimal listening experience. Image generation utilizes OpenAI's sophisticated visual models to create relevant and engaging visual content that complements the technical discussions. AI content has undergone human expert review for accuracy and coherence, ensuring that complex technical concepts are presented correctly and comprehensibly. However, we acknowledge that potential oversights may exist despite our careful review process, and we encourage listeners to consult original research papers for complete technical details. Our commitment to transparency includes providing clear attribution to all sources and maintaining high standards for technical accuracy. while making advanced research accessible to broader audiences interested in the future of artificial intelligence and robotics. Thank you for joining us on this exploration of the latest breakthroughs in computer science robotics. We've witnessed remarkable advances from curious autonomous vehicles that learn through environmental exploration to robots capable of ethical decision-making that balances obedience with safety. These 19 papers represent the cutting edge of robotics research, showing how artificial intelligence is creating machines that are not just tools, but intelligent partners capable of understanding and adapting to our complex world. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from arXiv preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer, this video uses arXivepreprintserver.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXivepreprintserver.org.